Hi, I'm the Octopus Lady. You're watching Alien Ocean, and let's talk about sponges today, shall we? Alright, so phylum Porifera, the phylum of the pore bearers. It's made up of over 9,000 currently extant, or still living, members, or maybe 8,000, or maybe 15,000. I don't know. The number kept changing depending on what source I was looking at. It's comprised of 4 different classes: Calcarea, which are the calcareous sponges; Hexactinellida, which are the glass sponges; Homoscleromorpha, which are the sponges? They're different from other sponges because they lack cell types that most sponges have. And then finally, Demospongii, which are, I guess, like the sponges, because they're the most common. Something like 80% of all sponges in the world are part of that class. Sponges are quite possibly the very first animal to ever exist. I thought that was true for a long time, but apparently there's been some fighting over that, with comb jellies stepping into the ring. Some people believe that they came first before the sponges, but I'm not here to get into that mess. What I'm basically trying to say is that sponges are really old. How old? Well, that's up for debate too. There is a paper that says that the oldest fossils that we have of sponges are 535 million years old, but there's another paper I read that said they might be 600 million years old, another that said they might be 750 million years old, and a very recent paper from 2021 says they might be 890 million years old, which is astonishing if that's true. And I don't know which number to pick, so we're just gonna do it like this with a bunch of question marks. And that means that sponges beat out jellyfish as the oldest organism we've talked about on Alien Ocean. Probably. Hey, Octopus Lady from the future here. So I'd gotten some comments on my last video about what I should call this corner, and someone suggested the fossil-free zone, which I really liked, so I'm going to be using that from now on. Thank you, Talia Smith, for suggesting that. Anyway, back to the video. Sponges, on the surface, aren't terribly complex animals. They don't really seem to do anything, except filter feed and reproduce. Take this sponge, for example. This is a sponge with an osconoid body plan, which means it's got a pretty simple body. It's sort of shaped like a vase, and this big empty space in it is called the atrium or the spongicele. Spongicele? Whatever, which is lined with a single layer of cells called choanocytes, and we'll talk about those in more detail in a minute. The outside of its body is covered by a single layer of flat cells called pinacocytes, and then in between we got the mesohyl, or mesohyl, or I don't know how to pronounce this word, which is this spongy substance. And there are pores that go through the entire body wall of the sponge where water gets pumped through. This pumping action is created by the choanocytes, which look like this. Every choanocyte has a flagellum in the center of it that is surrounded by extensions of the cell membrane, which are called microvilli. The flagellum flails and whips around constantly, which creates a current that pulls water through the pore. If there is any edible particulate matter in this water, it gets collected by the microvilli and eaten. Then the now filtered water leaves the sponge by getting pumped through the spongicele and out through the osculum. This whole system, by the way, is called the aquiferous system in sponges. And in general, that's it. That's what sponges do all day and all night. They filter water. Sounds boring, right? But y'all know I wouldn't be here telling you about sponges if they were boring. So osconoid sponges are really small. They can't get any bigger than about 1 millimeter in diameter. Tiny itty bitty sponges. This is because of, like, I don't know, physics stuff? Is this physics or is this just math? Whatever. Basically, when something gets bigger, its volume increases at a faster rate than its surface area. Sponges do all their filter feeding along one surface of their body, so if it gets too big, there won't be enough surface area to support the larger volume of sponge. Does that make sense? If it doesn't and you think you can explain it better, please do so in a comment. You nerd. The point is, when sponges are at their simplest, they need to stay really, really small. But we know that sponges can get huge. And in fact, some scientists believe that they are capable of indeterminate growth, which means that there is no upper limit on how big they can get. So how is that possible? Well, allow me to introduce you to leuconoid sponges. And their aquiferous system is super complex. It's this massive network of water vessels that permeate through a dense, spongy body. Without getting into all the nitty-gritty details, the biggest difference is that while osconoid sponges have choanocytes along one flat part of their body, leuconoid sponges are full of spherical chambers that are lined with choanocytes. And I mean full. Some sponges have been found to have 10,000 choanocyte chambers in just 1 cubic millimeter of their body, which means that the amount of surface area in a leuconoid sponge can keep up with its increased volume. And the reason why this body type can, in theory, cause indeterminate growth is because eating and breathing for a sponge is decentralized. It's not like food and oxygen collects in only one part of themselves, and then they have to figure out ways to get that stuff to the rest of their body. No, every time a sponge grows, that new part has all the infrastructure it needs to feed and oxygenate itself. And when every new part of you can basically independently sustain itself, then you don't ever have to stop growing. Of course, they do, because sponges grow into coral territory, and then they get into fights, and there's probably certain rocks that sponges don't want or can't attach to, and some animals eat them, but you know, like, in theory, they can grow forever. Sponges are also capable of infinitely rearranging their insides. Okay, so something that makes sponges really different from other animals is that none of their cells are stuck together. See, in most animals, all of our cells are like glued to or connected to each other in some way. I mean, not all of our cells, obviously, but like a lot of them are. There's no real way to disconnect these cells from each other without basically killing them. But sponges are like, nah, I'm made up of strong, independent cells who don't need no basement membranes. When small sponges are observed under microscopes, everything is moving all the time. The cells that make up the pinacoderm, which are called pinacocytes, they go crawling around the edges of new growth of a sponge. There are a bunch of different kinds of cells in the mesohele. Remember that? The mesohele? That are amoeba-like, and they're just moving all over the place. And entire choanocyte chambers and their associated canals get moved around too. Not the individual cells themselves. Entire structures are scooted around the sponge's body. The paper I was reading that was describing this doesn't know how they move, but the researcher did note that they were constantly surrounded by moving mesohele cells, so they might be the ones who are pushing the chambers and their canals around. And this is happening constantly. Constantly. You would think that after a while, when a sponge has arranged things inside of itself in a satisfactory manner, it would, like, you know, stop, but it doesn't. Sponges don't ever stop rearranging their insides. You could be looking at a full-grown, unharmed sponge under a microscope, walk away for a few hours, come back, and see that the sponge has moved everything around in a few hours. And on top of that, sponges are still somehow filtering the water for food while moving everything around, which to me, that has such big Mad Max energy. Like, it reminds me of how characters in Fury Road were fixing the war rig, the giant semi-truck they were all riding in, while they were driving it. Like, it's just wild to me that sponges are able to do this. Like, that's incredible. The cells of sponges differ from those of other animals in another significant way. Most of the cells that are currently inside your body are always going to be those kinds of cells. For example, your nerve cells are never not going to be your nerve cells, right? But sponges don't seem terribly attached to what their cells are at any given moment. In fact, a lot of their cells just aren't anything, but they can become everything. May I introduce you all to archaeocytes, which are amoeboid totipotent cells. Amoeboid meaning that they move around like amoebas, and totipotent meaning that they can give rise to lots of different kinds of cells. And if this sounds familiar to you, yes, totipotent cells are also called stem cells. But yeah, archaeocytes, when they divide to create more cells, oftentimes their daughter cells don't grow up to be other archaeocytes. They grow into all different kinds of cells that the sponge might need. Myocytes? Definitely. Lophocytes? No prob, Bob. Sclerocytes? I got you, fam. Choanocytes? Oh, actually, that's not one that archaeocytes can turn into. Oh, wait, just kidding. They totally can. Archaeocytes, baby. They can do it all. Hypothetically. Honestly, a lot of papers I read were like, archaeocytes are really hard to track because they move around a bunch. So we haven't seen them turn into all of these cells with our own eyes, but we think they do. So yeah, maybe take this list with a grain of salt. Well, except for one, we're pretty confident that archaeocytes give rise to choanocytes, and get a load of this. There is some evidence that choanocytes can revert back tubine archaeocytes, which I have never heard of that before. I've obviously heard of stem cells becoming other cells, but I've never heard of it going in the opposite direction. If this is true, there still seems to be some discussion happening around this, then that means that choanocytes are, in a way, totipotent cells too. Man, I hope that's true. That'd be so cool. Anyway, a sponge's ability to do all this significant inner restructuring is for two reasons. Well, probably more, but we're just gonna talk about two. First off, I mean, it's great for when you get injured. Oh, you lost an entire chunk of yourself? Well, it's fine. We got plenty of cells that can turn into whatever you need to fix that. And while new stuff is getting built, we'll just grab a few things we already have on hand and put them over here, and there you go. Already fixed some of the damage. In fact, this is seen as a kind of asexual reproduction in sponges. It's called fragmentation, and it's just when like fragments of the sponge are torn off and then get carried away or float to somewhere else, and then they just reattach to themselves to a rock and grow into a new sponge. Scientists have actually squeezed sponges through finely woven cloths, which broke these sponges down into fragments that were made up of just a handful of cells, and all those tiny bits grew up to be fully functional sponges. The second reason seems to be for optimizing water flow through the sponge, the rearranging aspect in particular. If one side of the sponge is exposed to faster or more nutrient-filled currents compared to the other side, then they just move everything over to that side. That's a bit of an exaggeration, but it means that sponges are way, way more efficient at gathering food for themselves compared to if all their cells were evenly distributed throughout their body. My favorite thing about sponges is how unassuming they are. No one thinks they're capable of much of anything, and on a macroscopic level, I will concede that yeah, sponges don't really seem to be capable of much of anything. But on a microscopic level, they're like one of the most dynamic and interesting animals I've ever studied, and it's nice to be reminded that just because something looks boring doesn't mean that it is. Thanks for watching another episode of Alien Ocean, and special thanks to all the new subscribers that are here and the new patrons. This happened real fast. Honestly, I thought my last video about siphonophores was going to become one of my worst performing videos, and that was so incorrect. And by the way, since that video made way more money than was expected, I do plan on donating some of it to the Hawaiian Environmental Alliance. I don't know how much yet, because everything is just, everything is just a whole lot right now, and it's great, and it's a little terrifying, and just thank you all for being here. Anyway, be sure to like, share, and subscribe. Check me out on Twitter and over on Patreon, where you can get early access to videos or your name in the beautiful credits. There's also the second channel, the Octopus Lady, where we stream the game Subnautica. And then finally, today's hopefully interesting question of the day is, if you could rearrange your insides in any way you wanted, how would you do it? Leave your answer in a comment down below, and until next time, this has been your friendly neighborhood Octopus Lady, reminding you that you don't have to go into space to find aliens.